Welcome to our concept for a climatic responsive facade to Building 215. Our group initially centered its investigation on an exploration of several precedent buildings in an attempt to fuse the appropriate elements into our case study project, Building 215 at Curtin University, Perth. However, prior to the precedent analysis, we identified the existing environmental and technological systems of our case study building. I was tasked with Theme 1, Energy Conservation. Initially, the thermal comfort for the internal occupants was explored. So too was the transfer of heat through the facade. Additionally, passive ventilation and the thermal mass of the unshaded facade was assessed. Finally, the acoustic performance of the existing concrete walled facade was calculated at RW50. With the addition of 30mm sound check, this provided an improved rating to RW65. Further, we proposed the removal of solid wall construction to a specific section of the plan. This was replaced with a double glazing system, which slightly outperformed the concrete wall. In addition to the acoustic improvements, this portion of solid wall construction, with no operable windows to the east and northeast elevations, resulted in a dependency on mechanical ventilation. Through the reconfiguration of some internal walls and full glazing and louvers, the previously mentioned areas, we were able to improve the passive ventilation and reduce the energy consumption of the HVAC system. Nonetheless, the most significant recommendation proposed to enhance the facade's climatic responsiveness was the introduction of a double skin. This was achieved by offsetting the original diagrid at a distance of 2 meters to accommodate the shower towers to the north elevation. We then infilled the diamond form of the diagrid with a combination of vegetation and screening. The screening was strategically positioned at a higher level to perform constant controlled shading to specific internal spaces. Initially, the screening took a linear form similar to our precedent building, the Surrey Hills Library in Sydney. However, through a collaborative design process, this element evolved into a hybrid blend of the self-shading detail observed in the South Australian Health and Medical Research Institute building and the aforementioned library. The resultant shading device takes the form of a more organic nature, which is also reflective of the newly proposed vegetation. The design recommendation to adopt the ancillary facade skin formed the essential components of the project, primarily facilitating necessary shading to the core building. It was observed in the Sapphire analysis that this observation resulted in an 8% reduction in overall energy consumption. We believe this is considerable, as the original building is already very efficient and achieves a 5-star Green Star rating. Thank you.
The proposal of a geothermal labyrinth system is expected to reduce cooling energy loads of the building by up to 25%. External air will first be drawn into the building from the roof, where it will pass over a heat exchanger containing cold water from underground thermal coils. These underground thermal coils are buried approximately 100 metres under the atrium and maintain a water temperature of approximately 16 degrees to 18 degrees Celsius all year round. As the air travels down through the new glass atrium, it undergoes a biofiltration process before it enters the labyrinth in the basement. As the air travels through the labyrinth, the cooling process continues until the air reaches the vertical duct. From here, the pre-cooled air is delivered directly to the existing HVAC system throughout the building. Adjoining the labyrinth in the basement is the addition of a new sewer mining plant. This hydraulic system is a major improvement, as it will now service the entire building's non-potable water needs. With the capacity to treat up to 100,000 litres of water per day, this system is environmentally sustainable and will reduce the load on the clean water supply significantly. The mining system is also crucial to the success of the new building envelope. The surplus water generated will be pumped from the water storage tank and used to irrigate the new vertical garden, which has been adapted onto the diagrid skin. A radical addition to the hydraulic system will be the 8 shower towers. The towers are an evaporative cooling system located within the double skin envelope of the north elevation. At 8 metres tall and 1.4 metres in diameter, the shower towers are a powerful statement of the building's environmental aspirations. From within the building, the transparent towers will play with internal ambient light conditions. From the outside, however, the towers are purposely hidden so they do not interrupt the form of the dominant diagrid. As a part of the hydraulic system, the shower towers will draw water from the rainwater tanks located on the roof. Positioned at the top of each shower tower, an atomizer nozzle will then release a fine mist of tiny water droplets into the chamber. As the water falls through the tunnel, the air above acts like a vacuum. This natural phenomenon causes the droplet to release its heat energy, with the remaining particles transforming into cool air. The end result of this evaporation process is the direct release of cool air into the internal public spaces. Testing revealed that the addition of the shower tower system will improve the energy efficiency by an extra 3%.
Curtin 215 Engineering Pavilion is a living laboratory. It is a vivid sample of sustainable building, about studying on-site electrical energy consumption, PVB panel system, and the structural stabilities to works we know. The existing building structure will be preserved, while there are 6 new building structures. They are structural metal frame, flat truss system, cross louvers, biofilter green atrium, curtain wall, and basement. For the structural metal frame, the diagrid forms a self-standing metal frame structure. It is extended 2 meters away at 4 sides, affixed to existing 4 slab to form a mixed structure in order to provide more stable and no-bearing supportings. Thus, thinner RHS can be used. Cross diagrid is reinforced with horizontal steels to resist the shear force. The loading force through the diagrid to the ground and other supporting elements, such as existing entrance cover frame and building surface extension at east. At the loft facade, the diagrid holds up the cooling towers and air duct. At west, there is a big exhibition atrium. It is created by a flat truss system with a 9-meter span. There are totally 6 flat trusses. They are supported by 4 RHS columns at right and the diagrid system at left. The Howley flat truss is used, which is 450 mm high with diagonal grid system. For the cross louvers, they are located at the top of diagrid. The design idea is come from the Shamri facade. It has many triangular shading fins. Each is different in depth, fixed on the triangular curtain wall system. It can enhance the interior atmosphere with different pattern of light and shadows. The cross louver is embraced by the diagrid and perfectly well on the supporting wine frame. and then simply has nuts and bolts installation to fix on the diagrid system. Another new structural feature is biofilter green atrium. They are a folded triangular curtain wall system. The bridge simply cut through the atrium to provide a special experience of enjoying nature. The folding triangular curtain wall attaches to the building envelope by lugs and bolts. The south facade will be changed to a new curtain wall system with IGU glazing in order to enhance the thermal comfort and building energy efficiency. A large louver system is at the top of biofilter atrium to provide the lateral ventilation. A new basement is added to install the labyrinth, a big thermal mass to control the internal thermal comfort. In order to reduce the noise, a thick concrete wall with sound absorption layers is proposed to the geoplant room and water pump room.
The proposal for the building integrated greenery for Building 215 comprises of a combination of two systems that have been analysed, assessed and selected carefully to suit the precedent building and merge harmoniously with the other integrated systems, which will form a cohesive design proposal for the facade as seen through the 3D walkthrough. The first system incorporated is the atrium proposal, which is based on the findings from Surrey Hills Community Centre and Library by FGMT. The atrium system is integrated with the thermal coils and air ventilation system. The integrated greenery within the atrium aids the air filtration process that takes place within the atrium as the air is drawn in from the top of the southern elevation, as seen and noted in the drawings. The atrium will be located as a middle section between the internal and external spaces of the building within the southern facade. The atrium will aim to create a green filtration system that reduces the noise, light intake and helps improve the overall quality of air within the building, as well as improving the overall well-being of the building's occupants and users. The second system that is incorporated within Building 215 utilizes the Jacob rope method in the likeness of One Central Park in Sydney. The green climbing walls are incorporated within the main diagrid of the building. The proposal expands on the existing diagrid and wraps it around all facades, incorporating building greenery using a hydroponic, self-watering system that utilizes an automated method of irrigation, which is timed and minimizes any water waste. The system incorporates the use of rainwater, which requires approximately a minimum of 0.5 liters of water per day per square meter, which is therefore a minimum of 300 liters of water per day, considering that the proposed green wall within the new diagrid spans approximately 600 square meters. The integration of climbing plants on the existing diagrid will help reduce the overall thermal gain within the building by acting as a bio-shading device within the facade, therefore reducing the solar heat gain and loss throughout the year, as the plants incorporated within the diagrid will be carefully selected so that they provide maximum shading during the summer and optimal light intake during the winter.